I think we should start.
Good evening, everyone. Thanks for joining us for today's webinar. I am Piyush Nosali, faculty in Building Technology and Construction Management Division in the Department of Civil Engineering at IIT Madras. For this webinar, we got very good response. We had more than 275 registrations, not just from India, from outside India also. Before we start today's lecture, let me take this opportunity to introduce our Prospective Center of Excellence at IIT Madras. So I will be just sharing a few slides. One second. Are the slides visible?
Yes.
Yeah, fine.
Yes.
So we have this Prospective Center for Excellence on technologies for low carbon and lean construction at IIT Madras. And you can see here the vision is to be the primary destination in India for all interested in developing and implementing ideas on low carbon and lean construction technologies. And we aim to develop India's first integrated test bed for evaluating the uses of agricultural, industrial, and construction demolition waste in concrete for directing practices, policies, and standards for waste reduction and in Indian construction industry. So we have a very interdisciplinary team here to address this challenge, which comes from construction materials, construction management, and building science. With the goal of reusing material waste, at the same time reducing process waste. That's also the focus of our PCOE towards achieving sustainable construction. So we are focusing on materials, different types of materials, and also process waste. And we have a system approach. We are looking at various aspects. You can see here, life cycle approach.
Zoom link, they have mail us.
And we have a dedicated web page. Please visit this web page to find more information about the activities of the center. And we are collaborating with experts worldwide. And we are planning to have these regular webinars on monthly basis. So watch out this space. And here you can see the web link and also email ID. Those of you who are interested in collaborating with us, I encourage you to reach out. Feel free to do so at any point of time. So let's get started with our lecture now. Just for your information, this lecture is being live streamed on YouTube. So please post your questions. We'll have some time to take a few questions at the end. And also the recorded lecture will be available in our YouTube channel. We have a dedicated YouTube channel for technologies for low carbon and lean construction technologies at IIT Madras. So it's my pleasure to introduce Professor Farshad Razabipur from Penn State University. Dr. Farshad is a professor of civil engineering at Penn State University. He is also the associate director of Center for Integrated Asset Management for Multimodal Transportation Infrastructure Systems, which is US Department of Transportation's Regional University Transportation Center. He received his PhD degree from Purdue University in civil engineering with emphasis on cementitious materials. And he has been active for last 20 years in teaching and research with a focus on developing sustainable building materials. Specifically, he performs research on low CO2 cements, unconventional pozzolans, concrete durability, alkali silica reaction, and ultra high performance concrete. He has authored over 100 technical papers and reports on these subjects. He's also a fellow of American Concrete Institute, and he's the cementitious materials section editor of ASCE Journal of Materials in Civil Engineering. He's quite involved with ACI, where he serves as a chair of Committee 236, which is on material science of concrete. And also he's the secretary of Committee 232, which is on fly ash and bottom ash in concrete. So without further ado, I now invite Professor Farshad to deliver his talk.
Thank you very much, Professor Chansoli. Let me see if I can, is it okay if I go ahead and share my screen?
Yeah, please do so.
Yeah, Piyush, I think you need to stop sharing first.
Yeah.
Yeah.
Okay, can you see my screen now?
Yes.
Okay, very good. Okay, good evening, ladies and gentlemen. It is a privilege to be the guest speaker at this meeting today and be in the presence of the esteemed colleagues and the folks from industry and academia that work on cement and concrete materials. As Professor Chansoli mentioned, the topic of my presentation today is on utilization of off-spec fly ash for low carbon concrete. Before I start, I want to acknowledge and greatly appreciate the outstanding work of my former PhD and current postdoc, Dr. Gopakumar Kaladharan, who has performed the research that I'm presenting today. He's also an alumni of IIT Madras, and he came with a lot of great background, and we were very happy to have him at Penn State over the last 4 years. And he's also here on Zoom today. So make sure you keep all your easy questions for me and the difficult questions for Gopal. I also want to acknowledge the funding for this research and also related research on the topics of low CO2 cements and unconventional pozzolans by Department of Energy, Federal Highway Administration, as well as American Concrete Institute. Okay, let me get my laser pointer started. All right, so in this presentation, I primarily talk about the off-spec fly ash in the form of fly ashes that have high sulfur content, or both high sulfur and alkali content. So the presentation has 4 parts. I'll start with motivation, then I go into sources and forms of So3 in fly ash, and then I'll talk about the impact of the So3 or high So3 fly ash on concrete performance, and then I'll finish with some conclusions. Okay. So many of us have seen a diagram like this, which shows a forecast of carbon dioxide emission for the rest of the 21st century. So this is annual emissions. Currently, we are at 40 gigatons CO2 per year, human-induced emissions, and it essentially shows different human development models and how much CO2 emission is essentially would be associated with those models. So, for example, the orange shows the status quo, and then we have some that are kind of a higher CO2 footprint models and some that are lower. There are prominent climate models that suggest that the Earth can sustainably handle only about 2 degrees C temperature rise in comparison with 1850 level or pre-industrial levels. And that suggests that to make sure that that 2 degrees temperature rise, so here we see the temperature rise associated with each of these models, and that suggests in order to stay less than 2 degrees C, we have to cut the CO2 emissions from today's levels of 40 to about 20, so by 50% by 2050. Okay. Now, if you look at cement and concrete industry, this translates to about an 8-fold reduction in the CO2 footprint per kilogram of cement. And the reason for this is that cement production has increased by more than 30 folds over the last 65 years, as we see on the graph on the left, which shows the material production in the later half of the 20th century until today. So the blue shows the increased use of cement, and comparing with the growth in human population, which has been about less than 3 folds. So this significant use of cement is because of primarily driven by developing countries that are building new infrastructure and new buildings to rightfully increase or enhance the quality of life of their citizens. And there is a lot of remaining demand in the world for this type of development. And as such, it is it is foreseeable that this current high levels of reliance or use on cement and concrete materials is going to continue in future. So at current rate, the cement consumption is forecasted to increase by a factor of 4 by 2050. And that means if we simultaneously want to cut the CO2 emissions by half from today, that means that we have to essentially do a factor of 8 reduction in the CO2 footprint per kilogram, which is quite an ambitious goal. I think most folks in this meeting know that the cement CO2 emission is one of the major causes of cement CO2 emission is so-called process emissions, which is essentially because of calcination of limestone. That makes up about 50% of the cement CO2 footprint. So the other 50% is because of the use of fossil fuels to heat the kiln, and some other CO2 release because of grinding clinker and other processes. So even if we use, for example, very energy efficient kilns that rely on renewable fuels, we are tackling this part of the pie and we are not touching the 50%. So there is kind of more broader approaches that needs to be taken other than just making better kilns or modernizing cement plants. Okay, so how to cut the CO2 footprint of cement and concrete? There are a number of very good work that has been done over the last 1 or 2 decades in this space. One thing that is important is that cement and concrete is used very broadly in many parts of the world, in both developed and developing countries, in some of the highly urbanized as well as rural parts of the world. And as such, for CO2 solutions to have a kind of a real impact, we need this broader adoptions, and we need to make sure that our solutions have a low cost, both in terms of the capital expenditure as well as the operational cost, and are also easily implementable by people with minimal training. So in light of kind of this criteria, these are some of the solutions that have been offered. Clinker substitution is something that has been actually worked on and suggested for a couple of decades now, essentially replacing cement with SCMs. And there are some that argue that we've already kind of fully utilized, or we've gotten all the benefits that we could have from the clinker substitution strategy, because not because we cannot take out more cement and put SCMs in a concrete mix, but because we are already using all of the usable SCMs in the form of fly ash or blast furnace slag. And really that, for this strategy to continue to make an impact, we need to make sure that we have reliable new sources of SCMs that are introduced in the market kind of globally. Others, and kind of the rest of my talk really kind of maneuver on this point quite a bit. Other solutions that have been suggested are, energy efficient kilns that are powered by renewable fuels, improving durability of concrete. So, we're reducing the demand for kind of renewing the structures or building structures frequently. Alternative cements using geopolymers, calcium sulfoaluminate cements, and so on. And also carbon capture and use technologies like carbon cure, solidia cements, and others that use CO2 curing and sequestration inside concrete. Okay. So as I mentioned, one of the main strategies is clinker substitutions, and that requires the availability of SCMs. So interestingly or unfortunately, right at the time that we need SCMs more than ever in the concrete industry, the supply of conventional SCMs are declining rather significantly. This is, as it comes to fly ash, this is primarily because of shifting away from use of coal to produce electricity, primarily for the environmental reasons. The graph that you see on the right-hand side is, showing the fly ash production and use in the United States from the start of the century. And if you look at, 2008 levels until today, we see that by these kind of a dark blue bars, that the fly ash produced in the United States has actually declined by near 60%. And there is a forecast that by the end of this decade, the supply of freshly produced fly ash is not going to be even half of the demand by the concrete industry. So 14 million ton supply versus 35 million ton demand. So this kind of a supply-demand gap requires, discovery and utilization of alternative SEMs. Again, there is a lot of great work that is being done in this space. The work that has, including the work that has been done at IIT Madras on some of these alternatives. So-called harvested ash or harvested fly ash that have been stored in landfills and ponds. Off-spec fly ashes that are currently not being used in concrete because of the high loss in ignition or high SO3 content. I'll talk a lot about these kind of the high SO3 in these two types of fly ashes, the fresh off-spec ash as well as the harvested ash. Other types of materials such as ground bottom ash, calcined clay, limestone powder, volcanic biomass ash, things that Professor Chansoli mentioned as part of the mission of the Center of Excellence at IIT. Okay. All right, so what the objective of this work is really to make high SO3 fly ash, both fresh fly ash and harvested fly ash, safe and available for use in concrete. And we do so by studying how the form of SO3 as well as the content of SO3 impact the performance in concrete, by developing beneficiation technologies to mitigate areas of negative performance. And we also look at both high SO3 fly ash as well as fly ashes that are high in both SO3 and alkalis. Okay, so let me now talk about sources and form of SO3 in fly ash. The question is, where does SO3 in fly ash come from? The short answer is it comes from coal. Coal can contain pyrite, gypsum, or organic types of sulfur, which when coal is combusted, these are oxidized in the form of SO2 or SO3 gas, and they are emitted from the smokestack or the flue gas. The air emission regulations would essentially cap the amount of SOx that can be emitted, because it's highly hazardous, causes acid rains and other problems. And because of this, most power plants have a so-called an FGD or flue gas desulfurization unit that is installed as part of the flue gas. So as we see here, as the flue gas is coming from the boiler, along with technologies to capture the fly ash and to reduce NOx, we have to reduce this SO3 gas. Excuse me. And these technologies could be wet or dry or semi-dry, and essentially they are based on exposing or injecting the flue gas with a so-called SO3 sorbent, which can be calcium carbonate or calcium hydroxide or sodium carbonate, which would capture the SO3 in the kind of a form of a calcium or sodium sulfate salt, then that particles are removed either together with fly ash or separately, depending on whether you have a wet system or a dry system. All right. In addition to conventional power plants, there are so-called these fluidized bed combustion or FBC power plants that inject limestone powder directly into the boiler, and that limestone is converted into anhydrite, and that anhydrite is collected with fly ash. So there is a lot of sources of so-called FGD products commingling and contaminating fly ash. In addition to this, you can have post-production contamination, which are prevalent in the terms of, in the form of landfill or pounded fly ash, that when this fly ash was produced, maybe 2-3 decades ago, it was stored together with or kind of mixed together with FGD materials in the same landfill. So now when you're harvesting that fly ash, you have to either separate the FGD materials, or you have to somehow sequester them and make sure they are neutralized. So for the next few slides, I'm going to use these abbreviations, the HSFA, which stands for the high sulfur fly ash, and then the HSAFA, which stands for fly ash that has both high sulfur and alkalis. All right, a quick note on the fluidized bed combustion fly ash. So this is a technology or a special type of boiler that is designed to burn so-called waste coals. These are coal pods that have about 30%, 25 to 30% carbon only, or coal content only, and the rest is essentially clay and dirt, if you will. This is burned at a temperature of about 850 degrees C, which is about half of the temperature of conventional power plants. And this low temperature allows a lower thermal NOx emission, which is beneficial. It also allows cleanup of waste coal pods that may be laying around in many parts of the world, such as in Eastern United States. To scrub out the SO3s or SOXs, limestone powder is injected directly into the furnace, which captures the SOx in the form of anhydride primarily that commingle with fly ash. The other issue with these fly ashes, or the other attribute of these fly ashes, is that because of the low combustion temperature, the clay phases do not melt, but essentially they become calcined, and they retain their angular and porous particle shape, as we see in the SCM micrograph over here. And that can lead to a higher water demand, or kind of higher demand for water reducing admixtures in concrete. All right, so this flowchart kind of summarizes the type of FGD contaminations that you can have in fly ashes with high sulfur or high sulfur and alkalis. So in conventional power plants, you may have calcium-based sorbents in the form of calcium hydroxide or calcium carbonates that are injected into the flue gas, and they form predominantly calcium sulfite, or so-called mineral hennebekite, in the fly ash. You can also have sodium-based sorbents, such as sodium carbonates or Trona, and they predominantly make thenardite or sodium sulfate that would be present in fly ash. And then you also have the FBC power plants that use primarily calcite as the sorbent, and predominantly they form calcium sulfate in the form of anhydrite or gypsum in the final fly ash. Now, I argue that in addition to the SO3 content, the form of SO3, whether it's calcium sulfate or calcium sulfite or sodium sulfate, can have a large impact on how these fly ashes perform in concrete. So if we look at it, kind of summarizing, some of these impacts, calcium sulfate is a slightly soluble salt. It is used in cement to essentially regulate the hydration of C3a. And it has variable effect on strength development depending on the dosage that is used, and is usually optimized the content to get maximum strength development. At high dosages, it can form ettringite and cause volume instability. Calcium sulfite, on the other hand, is a material that is much less research has been done on this area. It's a salt with a much lower solubility. There is suggestion that it may regulate C3a, but the effects are not very well known. The effects on strength are also not known. There is suggestion that they can form sulfite AFM phases as opposed to sulfate AFM phases, and this may or may not cause a volume increase. Finally, sodium sulfate is a very highly soluble salt. and can essentially dissolve into the pore solution and increase the alkali content and also increase the OH content or the pH of the pore solution. And by doing so, it can accelerate the setting. It can increase the early age strength. Usually it comes at the cost of later age strength. It may destabilize ettringite and favor AFM formation because of high pH. And very importantly, because of the high pH, it can cause ASR, or it can diminish fly ash's capability in reducing ASR. Here I have a summary of the existing ASTM standards on essentially limits on So3 and fly ash. So the ASTM C618, which is the standard specification for fly ash for using concrete, put a maximum 5% So3 limit. In fly ash, there is no limit on alkali content. And this 5% So3 limit is essentially adopted based on Portland cement specifications. There is also ASTM C595, which is the standard specification for blended cements, and it imposes a 4% limit on the So3 content for blended cements, for example, for type 1P, which is type 1 pozzolan. And it allows for higher So3 contents if there is a kind of a lime water expansion test, so-called ASTM C1038, which I'll talk about towards the end of today's presentation. If the expansion is less than 0.02% at 14 days, it allows for higher So3 contents. Finally, the ASR spec, ASTM C1778, it really doesn't pay attention to the So3, but for the alkali content, it put a cap of 4% for fly ash and preferred 3%. And this is to ensure that there is a low pH for mitigation of ASR as a result of use of such fly ashes. Okay, yeah, sometimes the slides don't advance very quickly. All right, very briefly, the literature on use on looking at high sulfur fly ashes is fairly limited. We've found two, I would say, main studies that focus on these high sulfur Hanabekite or calcium sulfite containing fly ashes, and kind of very briefly, they both suggest that one of the main issues with the use of these fly ashes is a significant setting time delay. They don't explain the reasons or how this can be mitigated, but they report that the presence of Hanabekite can cause setting delay of Portland cement mixtures. All right, so now let me talk about essentially our work on looking at how the So3 type and So3 content in fly ash would impact concrete performance. So to answer this question, we tested both doped fly ashes as well as real fly ashes. So a doped fly ash means that we picked a spec fly ash or a specification compliant fly ash, which had as a control, and then we added to the So3 content of that fly. That fly ash had about 0.8% So3 content, which is well below the 5% limit. We added to the So3 or by kind of blending that fly ash with gypsum and hydride calcium sulfide or sodium sulfate in order to raise the So3 content to 3% all the way to 11%. And by we also made cement paste and mortar mixtures with 20%, with 80% Portland cement and 20% of such doped fly ashes. And that means that the total binder So3 content was 3.75% all the way to 5.35%. These So3 levels were essentially chosen based on the reported So3 contents of off-spec fly ashes in the literature, and they represent So3 values both above and below the ASTM limit of 5% in the fly ash. And also they represent So3 contents above and below 4 to 5% of the binder, the total cement plus fly ash, which can cause deleterious expansion. As I mentioned, we also tested real fly ashes. More specifically, we looked at 5 real fly ashes. the spec fly ash, which we used as the control. We looked at two so-called high sulfur fly ashes that contained calcium sulfite. We looked at an FBC fly ash, which contained anhydrite, and we also looked at a Trona Fly Ash, which contained sodium sulfate. The table shows different properties of these fly ashes, the sum of silicon, aluminum, iron oxide, calcium oxide, sulfur, and so on. And the red shows the areas that essentially the ASTM limits were violated. So you can see for sum of oxides, for the HSFAs, we're slightly below the 50% limit. 3 of such fly ashes classify as class C fly ash based on their calcium oxide content, 2 classify as class F. We can see the 4 off-spec fly ashes all have a high SO3 content above the 5% limit. The Trona Fly Ash also have a high alkali content. Other properties are more or less in line with ASTM requirements. All right. We also did a quantitative mineralogical analysis using quantitative X-ray diffraction. So on the left-hand side, you see the fly ashes that contain Hanna-Beckites. So you can see that they have about 60–63% amorphous phase, and then quite a bit of this Hanna-Beckite phase, the calcium sulfide CaSO3, between 17–20%. They also contain quartz and some other minerals. The FBC fly ash is about 50% amorphous. There is quite a bit of quartz. As I mentioned, this is a very impure source of coal, so it comes with a lot of dirt, if you will. So you have quartz, muscovite, hematite, other impurities. There is quite a bit of anhydrite in this as well, which comes from the CO2 scrub, or rather SO2 scrubbing. Finally, the Trona Fly Ash is about 64–65% amorphous. There is a phase called Burkite, which is essentially the remnant of the Trona that was injected for SO3 scrubbing. You also have quite a bit of sodium, or a considerable amount of sodium sulfate here. You have quartz and some other minerals. We looked at setting time, we looked at pore fluid pH, we looked at workability of mortar, compressive strength of mortar, expansion. We also have some tests that are currently ongoing or are planned, such as sulfate resistance, some of the more characterization tests such as calorimetry, X-ray diffraction, and SEMs. And I'm going to share some of these results with you in the coming slides. Okay. So first, let's look at the impact on the time of setting, which was measured by BICAT. The graph on the left shows the initial time of setting. The graph on the right shows the final time of setting. So the y-axis shows the setting time versus the SO3 content. These are all doped fly ashes. So for the plain Portland cement mix, we had about 140 minutes. For the mix with 20% of the controlled fly ash and 80% of the cement, the initial setting time didn't change much. And then if you look at, those so-called doped fly ashes where we blended this controlled fly ash with, sulfur-bearing compounds, you can see the impacts essentially using based on the rest of the graph. So for example, the blue, which shows the Hanna-Beckite contaminated fly ash, shows that by introducing the Hanna-Beckite, the time of setting tend to increase. So there is a delay in setting. On the other hand, if you look at sodium sulfate, by adding sodium sulfate, the time of setting tend to decrease or gets accelerated, both the initial as well as the final. For the other two, which represents gypsum addition or anhydrite addition, the effect is mixed. At low dosages, we'll have some retardation. At higher dosages, we'll have some acceleration of the setting. Okay. Now let's look at some real fly ashes. The bar chart shows the initial and final time of setting. This kind of a medium blue shows the Portland cement mix. The brown shows the controlled fly ash mix. And then we see that when instead of using control fly ash, when we use an FBC fly ash, which contains anhydrite, there is a delay in the initial time of setting, there's also a delay in the final time of setting compared with the controlled fly ash. If we use the fly ashes that contain Hanabekite, the HSFA 1 and 2, there is a significant delay in setting, as we see by this bar and that bar, both in the initial and the final time of setting, which is consistent with the limited literature or limited studies that were performed in the past. One interesting observation is that we can use a kind of an efficient accelerator, such as calcium bromide, to mitigate this or to kind of offset this setting delay. And essentially by using this type of admixture, we can see we can bring the setting time close to what would be expected from a controlled fly ash, both the initial set as well as the final set, as we see by this bar, that bar, and this bar. Now, if we look at the setting of Trona fly ashes, again, the initial setting of the Portland cement system, the controlled fly ash, and then when we use a Trona fly ash, we see a rapid reduction of the setting time, so flash setting or false setting, and both in the initial set and the final set. And this rapid setting is likely due to the presence of the sodium carbonate. As I mentioned, there is Berkite, which is the remnant of the Trona in this type of fly ash, and it seems like a lot of the Trona impacted fly ashes have remnants of Trona or sodium carbonates in them. And that sodium carbonate can react rapidly with calcium aluminates in cement and form carbonate AFMs, which can cause either a false set or flash set. You know, our work suggests that it's more of a false set because it can be recovered by remixing of the concrete. But fortunately, there is a good solution for this. And the good solution is that if you introduce a highly soluble form of calcium salt, such as calcium acetate, as we see over here, to the system that contains these soluble carbonates, the calcium would react with the carbonate and precipitate out as calcite. And as such, the carbonates are no longer available to react with the C3a. And we can see in the graph that can essentially fix the setting issue to a good extent. So the initial setting as well as final setting that are largely recovered by the addition of this calcium acetate salt. There are other forms of calcium salts that could also serve this purpose. Okay, next slide if my computer likes to do. Okay. Here I'm going to show some quantitative Xrd data on these on pastes, or essentially these are pastes with 80% cement, 20% fly ash. They were sealed under a dome, and we performed frequent Xrd analysis with an external standard, over the first 24 hours of hydration. So, for example, the graph on the left shows the mass of C3s as a function of time for the 24 hours. The orange color shows the controlled fly ash. And then we see that, for example, the fly ashes that contain Hanabekites, which is HSFA 1 and 2, these two lines, they have a significantly lower consumption or reaction of C3s, up to about 12 hours. At 24 hours, it seems to recover to a large extent. So we can see that kind of a lower C3s reactivity kind of goes hand in hand with the delay in setting that we see in these mixes. And we see similarly on the Portlandite formation. Again, if you look at the control, which is the orange over here, the light blue and the red, which are the Hanabekite containing fly ashes, up to 8 hours, there is very little Portlandite formation. At 12 hours, there is some recovery. And then at 24 hours, they are, kind of closer with the control system. Now, if you look at other kind of minerals within these systems, if you look at, for example, the C3a consumption, one thing that stands out is this dark blue kind of separating from the crowd for the first 12 hours, and that's a Trona Fly Ash. So we see the Trona Fly Ash is really kind of accelerating the consumption of C3a. If we look at ettringite formation kind of side by side, we see that the Trona Fly Ash is also kind of accelerating formation of ettringite for the first 24 hours. Also, here we're looking at some gypsum and other sulfur-bearing phases in the system. So the graph on the left shows the gypsum content as a function of time. The Portland cement that was used essentially contained hemihydrate as the form of sulfur in it, and this hemihydrate was hydrated to gypsum. So you see a kind of a spike in the gypsum content within the first hour of hydration. If we look at the orange, which is the control fly ash system, we see the gypsum is kind of peaked at about 1 hour, and it drops down to 0 at about 12 hours, which is very typical of what we expect Portland cement systems to do. Now, if you look at the case of the Trona Fly Ash, we see this gypsum consumption is accelerated and is dropping and disappearing at about 8 hours. And this kind of, again, goes hand in hand with the rapid formation of ettringite, which also explains the kind of a more rapid setting of the Trona Fly Ashes, as well as some of the rapid strength development data that I'm going to show you very soon. The rest of these kind of lines shows the green shows the case for fluidized bed combustion ash, and the other two shows for the Hanabekite containing fly ashes, which seems to kind of show a slowdown in the consumption of gypsum, but all of them kind of run out of gypsum at about 24 hours. The graph on the right-hand side shows some of the other sulfur-bearing phases. So, for example, these two lines show the percentage of Hanabekite in the systems that contain Hanabekite, and we see that essentially there is not much consumption of Hanabekite for the first 24 hours. We're going to do these studies later on, at later ages, to see, how reactive this Hanabekite is at later ages. The green that shows the FBC essentially shows that there is the FBC containing anhydrite. There is quite a bit of anhydrite that is present and is kind of being consumed, essentially converted to gypsum, as we see here, and both are consumed by 24 hours. All right, now let's look at pore solution results. So here we see the pore fluid pH as a function of time: 0 days, 7 days, 28 days. For the plain Portland cement system, we start at about pH of 13. The pH goes up to about 13.9. This is a fairly high alkali system. The pH is, more or less the same at 7 and 28 days. Essentially, any pH that is above 13.5, there is a fairly significant risk of ASR if there is a presence of reactive aggregate. So we see that this cement by itself could cause ASR. Now, if we replace the cement with 20% of controlled fly ash, we see that the 7 and 28 day pH has dropped slightly, which would help with ASR, but it hasn't dropped enough to kind of completely mitigate ASR. And then when we use a Trona Fly Ash, which has calcium, which has sodium sulfate, we see that the pH at 7 and 28 days is significantly increasing to values above 14, so much higher risk of ASR with this type of fly ash. Also, the rest of the bars are fly ashes that are doped with sodium sulfate. Again, we see as the SO3 content goes up, the pH goes up, the higher the ASR risk. Now, so the question is, what can be done about this? Well, fortunately, there is a solution. We've actually worked as part of a recent project. We've developed soluble salt admixtures that can control the pH of concrete. An example of such soluble salt is calcium acetate, which I already touched on before. So if you have a system, if you have let's say a pore solution with a high sodium hydroxide or potassium hydroxide content, high pH, if you introduce this soluble form of calcium salt, the calcium can react with the OH and precipitate out as Portlandite, and in doing so reduce the pH. while the sodium and the acetate or the anion of the calcium salt that was added essentially stay in the pore solution. So by doing so, you can significantly reduce the pH below the 13.5, which is the threshold for triggering ASR. So in the case of controlled fly ash, going from here by admixing 2% calcium acetate, we reduce the pH. Magnesium acetate can also do the same in the case of Trona Fly Ash. Again, by adding calcium or magnesium acetate, we can reduce the pH to kind of safe levels. Now, if you say, well, this is nice, but I want to see an actual proof of ASR mitigation, here's that proof. So these are some ASTM C1293 data, which shows essentially concrete prism test ASR expansion with a rather highly reactive aggregate, which is kind of a very highly expansive. And then when we add these pH controlling admixtures, we could essentially reduce ASR to below the failure threshold of ASTM, so to the safe levels. All right, let's quickly look at some of the other parameters. We'll look at the effect of So3 on workability in the thermal mortar flow. Again, controlled fly ash had about 120% mortar flow, and then we see that addition of gypsum or sodium sulfate can increase the flow slightly. Hannabekite and anhydride can decrease the flow slightly, but overall, the flow is not much affected, is more or less within the precision limit, with the exception of this one point, which is the FBC fly ash. And the FBC fly ash is impacting flow, not because of its SO3 content, but because of the fact that its particles are not sphericals. They are angular or subangular, and they have internal porosity, which kind of increases the water demand of the system. We also looked at the flow retention or workability reduction versus time for both doped fly ashes and real fly ashes. And kind of the short story is that the slope of these lines are more or less the same. The lines are parallel. So you may start at a slightly higher flow or lower flow, but the flow reduction with time is more or less the same, irrespective of the SO3 content. Then we looked at strength from early age 1 day to later age up to about 91 days. And we see that in the case of 1 day, control fly ash level is shown by this red dashed line. The addition of sodium sulfate or Trona type fly ash would increase the early age strength, while the other fly ashes have more or less similar strength comparing with the control. At 7 days, everything is more or less the same. That kind of a benefit, the early age benefit of the Trona fly ash is gone. Same at 28 days. And at 91 days, we see now that we are essentially paying for that additional early strength of the Trona fly ash or the fly ash with sodium sulfate by having about 10% or so less strength in the case of that fly ash. Other fly ashes are more or less comparable with control. Finally, I want to show you the so-called expansion under lime water. So this is ASTM C1038. This is a test that is looking at whether the excess sulfate or excess SO3, I should say, can cause ettringite formation and volume instability in mortar, and by extension to concrete that is exposed to water. So you make mortar bars, you cure them under lime water for 2 weeks, and you look at expansion. And here we see, as a function of the SO3 content, the expansion, the failure threshold is 0.02%. And we see that in the case of anhydride or gypsum contaminated fly ash, at very high dosages of about 11%, there is a risk of deleterious reaction, or we're going to cross the threshold, but everything else is kind of staying within the safe limits and innocuous limits. Okay, so to summarize the results, here's a table. The top part of the table, we look at the fly ashes that are essentially contaminated by anhydride or gypsum. An example of such is FBC fly ash. There is some retardation in the setting time by about 50%, which can be fixed with use of accelerators. There is some reduction in the flow in the case of FBC fly ashes because of their angularity. maybe a slight reduction in the one-day strength, but really the main sticking point with these fly ashes is that at very high SO3 content, above 11%, they can result in volume instability, which is kind of a subject of our ongoing work to kind of establish this limit a little bit firmer and see if there are ways to mitigate this issue. The fly ashes that contain Hanna-Beckites, such as HSFA 1 and 2, the main issue is that they can cause a fairly significant retardation. Again, this is largely addressed by the use of effective accelerators. Otherwise, they are pretty much good. They have a slight reduction in the early age strength, but they recover very quickly. In the case of fly ashes that contain sodium sulfate, such as a Trona Fly Ash, there is an acceleration in setting. You can even get false set or flash set if you have remnants of Trona or soluble carbonates present in that fly ash. This can be addressed by adding calcium acetate or other salts of soluble calcium salts to bind the carbonates out of the pore solution. The other issue is a significant pore fluid pH increase, which can lead to ASR. And again, this can be fixed by use of pH regulating admixtures. They generally give you some benefits in terms of early strengths at the cost of a later age strength, which again can be kind of designed for by kind of tweaking the water cement ratio and things like that. All right, so to kind of wrap up, I mentioned about the future work in conclusion. So currently we're looking at a better understanding of how the SO3 is impacting the setting and early hydration and the causes of the impact on setting. You're looking at calorimetry, pore fluid analysis, X-ray diffraction. We're also looking at more longer term impacts in terms of volume stability, sulfate resistance, and again, how these can be mitigated. We also are going to look at how the SO3 content would impact performance of water reducers and air entrainers. And finally, looking at upscaling this technology to concretes, to kind of field implementation and technology transfer. All right, so some concluding remark and take-home messages. Lowering concrete CO2, of course, very important. And one of the main pillars of doing so is a reliable supply of SCMs, which could be challenged if we are looking at only conventional SCMs. So we really need kind of new reliable supplies, large quantities of new SCMs. One such SCM could be a high SO3 fly ash, both in terms of fresh or harvested fly ash that has a very good potential. In our opinion, the ASTM's current limit of 5% SO3 is not the best criteria. It is actually somewhat overly conservative, and also it does not account for the form of SO3, and the form of SO3 can make a large impact on how that fly ash performs in concrete. We know that calcium sulfite primarily can cause set delays, but it can be mitigated by use of strong accelerators. Calcium sulfate may cause volume instability at very high SO3 contents. And the sodium sulfate primarily has two issues: the ASR risk, which can be mitigated by pH regulating admixtures, and it can also cause, if there are soluble carbonates that are present, it can cause rapid setting, which is also something that could be addressed by use of admixtures. Okay, so with that, thank you very much for your time and attention, and I'll be happy to answer any questions.
Thank you, Farshad, for an excellent lecture. Before we go for question and answer session, I apologize to our YouTube listeners. There's some issue. So anyway, we'll have this recorded lecture on our YouTube channel. We'll send email to all those who registered because of some issue in the initial 15-20 minutes with the live streaming. So anyway, this will be made available. So now I request those who are here, please unmute and ask a few questions.
Piyush, can I go first?
Yeah, sure. Go ahead.
So thank you, Farshad, for an excellent talk. I think you brought together some of the aspects of fly ash that not many people, at least in India, we're not quite familiar with many of these issues. Now, to bring things in perspective, am I right in saying that as we go towards technologies to reduce the SOx emissions, we will deal more and more with off-spec fly ashes? Am I right in saying that?
Yes, absolutely. I agree with that.
Okay, so it's not just, we are not just talking about the off-spec in terms of fly ashes that are available in ponds, for instance, but we are also talking about fly ashes that are collected in the electrostatic precipitators, which may have a lot more of the sulfur-bearing compounds.
Absolutely, yes. Both fresh fly ash and ponded fly ash, and I think depending on the region of the world or country, there may be kind of a more acute case for one versus the other.
Okay, okay. I just want to also talk about the aspect of the Trona Fly Ash, which seemed to produce very interesting characteristics. I think you had, there's also a significant bit of sodium carbonate in there. Is it?
Right.
And,
yeah, that, sorry, go ahead.
No, and is the carbonate sort of leading to a increased, I mean, dissolution levels of the aluminate? What's going on there?
Well, I mean, I mean, we experienced with, I mean, there is one set that is shown here, and I believe, Gopal, correct me if I'm wrong, we looked at other Trona impacted fly ashes too, that seems to, you know, power plants, of course, they are kind of focused on optimizing their operations, and then they care very little, if at all, about the fly ash. So they usually turn to end up kind of overdosing the Trona in, you know, when they are doing their scrubbing, and as such, some of the Trona or some of the sodium carbonate or alkali carbonate may remain unreacted in the fly ash. Essentially, you run out of the sulfur, and then, you know, everything else is going to be sodium carbonate. So our, you know, work, you know, at least till now, suggests that this could, I mean, if you look at that, this could accelerate the reaction of the aluminate, and interestingly, show kind of an increased formation of ettringite at you know, first 24 hours. Now, you know, we have calorimetry tests that are currently ongoing, and I think we need to kind of pay attention a lot more to this issue. But yeah, there is this issue of soluble carbonates that can cause you know, early age performance issues.
The other question I had was primarily related to the fact that when you tested the lime water expansion, so in this test, essentially, you're looking at a saturated lime water solution. Is that what it is? And is there a temperature also which is regulated in this test?
Yes, it's a saturated lime water. Is it 23C, Gopal?
Yes, it is 23C.
Oh, so it's at controlled temperature. Okay.
Right.
So it's not like at 38 degrees or something.
No, it's not
No.
increased temperature.
Yeah, and we have, I mean, kind of, this is a leap for Gopal. We also have and are testing these for extended period of time beyond 14 days. So Gopal, what have you discovered? Are some of these expanding significantly past 14 days?
No, actually, the expansion is sort of stabilized for most of the dope fly ashes. But for some of the real ashes, like the HSFA 1 and 2 and the Trona Fly Ash, for example, they are showing a little bit of expansion even at later ages, but it's still below the limit. So, yeah.
And one last question. I think it's very interesting to see that you are using additives to sort of bring the sulfate into or rather to reduce the potential for the alkali silica reactivity. I think that's an interesting line of action that you've taken there. So
Yes.
what was the, I mean, basis that got you started in that direction?
That's actually an interesting story. So it's Well, one is on kind of the technical need or demand. You know, in the US, and I think in many parts of the world, pozzolans are used as the primary vehicle for ASR mitigation. And there is, I know in North America, there is a lot of emphasis over the last decade or more on ASR and kind of discovering cases of ASR where in the past, you know, there was a belief that there is no ASR and so on. And that coincided with the reduced supply of pozzolans. So there is this kind of ongoing question of what we can do to mitigate ASR. At the same time, the other solution, which is lithium admixtures, of course, is a high demand by essentially battery industry. And so there is this kind of a vacuum of technologies to address ASR in case a pozzolan is not you know, available, or maybe to improve marginal pozzolans to kind of help them in mitigating ASR. We actually started looking at the effect of aluminum or aluminum-bearing compounds. A few years ago, we were looking at aluminum hydroxide as a potential solution, and it does actually work, albeit at significant dosages. You know, you have to like replace about 20% of your Portland cement with aluminum hydroxide, and preferably with an amorphous form of aluminum hydroxide to do that. And then we kind of gravitated towards more soluble forms of aluminum salts, you know, to essentially supply the aluminum for ASR mitigation. And then we kind of came across this idea that there is a way to actually fairly effectively regulate pH by precipitating out OH. And we looked at you know, we looked at a database. There is a cement and concrete composite paper that kind of talks about all of that. It came out a few months ago, and Gopal is the lead author. So we looked at some 700, we considered some 700 salts, soluble salts in concrete, and we kind of used a methodical way of narrowing down the list. You know, finally we came up with a list of 8 salts, or primarily calcium and magnesium salts, which we think have a lot of promise in regulating the pH and mitigating ASR. These are actually listed here. And Gopal also, as part of his PhD, has done a lot of work on looking at how these salts would impact other kind of attribute of performance of concrete, from fresh properties to strength to other forms of durability and things like that. And these are in his dissertation, and we're, you know, we will be submitting a paper on that soon.
Thank you. Excellent. Thank you.
Thank you, Mona.
Yeah. Any other question for Prashant? Please unmute yourself. We have time. I will get started. Just I have a few questions. Very excellent. I mean, excellent work. So I think among these 4 fly ashes, BC and you know, 3 others, I clearly see difference in the amorphous content, right? One is around 46% and rest are around 60 to 63%. So did you see any difference in terms of reactivity of these fly ashes? Or was there any direct correlation or?
Yeah, I mean, that's a good question. I mean, we don't have any report on reactivity of this, you know, except for the strain activity index, which is kind of the kind of highly imperfect way of measuring reactivity. There is a parallel work where we are looking at some of these pozzolans. I believe this FBC fly ash is part of it, but the others are not. And you know, the pozzolanic reactivity per se, I mean, if you look at exclusively pozzolanic reactivity is slightly lower, but you know, there are other forms of it, like for example, the presence of anhydrite that can lead to some strand development and things like that, that can somewhat kind of complicates or compensate for that lack of reactivity. But I think overall, maybe as I'm kind of thinking more about this, I think this is a good, your excellent suggestion to look at kind of pozzolanic reactivity of these ashes beyond just strand activity index and look at, you know, maybe R3 test or things like that.
Yeah, thanks. Other thing is, I noticed, you had a lot of quantitative Xrd results. It's very tricky to quantify these phases. Also, when you compare, at different time, your bound water is changing. So I'm assuming all these results are normalized, although it was not clear from the ordinate there.
Right. So Gopal, do you want to kind of address that question? That falls under the difficult questions that I punt to you.
Sure, I'll talk about that. Yeah. So we basically followed the procedure that is given in the practical microstructure book that was released by TFL. So the bound water content estimation is typically required when you use like an internal standard method where you do solvent exchange. So in our case, we just normalized it based on water to cement ratio because we used an external standard method, and our paste was, the hydration was never stopped. It was sealed inside a dome with the airtight seal so that we don't have to stop the hydration or there's no carbonation.
Right.
So using the external standard method, we were able to avoid that.
Okay,
But yes,
yeah.
we
If you have not,
definitely-
yeah, I got it. If you have not stopped hydration, then I think it's fine.
Yeah.
Also, this difference, is this significant enough? I mean, few percentage difference. Have you looked at different multiple samples to conclude that?
So for the C3s, we thought it is definitely significant because of the amount of difference between the things. But the other ones, yes, I do need to repeat. I'm planning to repeat some of these experiments to see what is the actual spread on these values so that we can figure out if that's significant or not. So
yeah, I think that's an excellent point. And I was kind of practicing the presentation yesterday and kind of putting some of the data or moving things around. I was thinking exactly about that, of how significant or how variable these data could be. I think especially for the ones that are, like when we're talking about single digits, then the spread may really not be statistically significant. Yeah.
About this So3 AFM phase, have you done any work on that just to check if it exists or if it is there, or is there a plan? Is there any plan to do so in future?
There is plan. So Gopal, correct me if I'm wrong. There is plan to do this in future. So it's I think that the XRD that was done till now was primarily focused on the first 24 hours, and we did not detect this phase. But it is I would say at least possible, if not likely, that we would see something like that at later age, as we kind of get conversion or we run out of the etching or the gypsum in the system, and you would kind of expect to see these AFM phases more.
Yeah, thanks. I think one of the questions I picked up from YouTube is it's about carbon content, what is the impact of the carbon content present in these ashes?
Well, the carbon content, as you see here, LOI is a surrogate test for the carbon content, and you see that all of these are kind of in a moderate level, certainly below or within the allowable limits of ASTM. In my opinion, there is no direct interaction between the unburned carbon and the sulfur in the fly ash. So these are kind of parallel issues. Of course, if you have a high LOI fly ash, you can, especially if you have variability in the LOI as a function of production time, you can cause problems with air entrainment. You can cause with, kind of non-reliability of your strength and your air and all of this stuff that we already know. Remediation or beneficiations for LOI would be needed, in the form of either a burnout which tend to be rather expensive, or maybe neutralization of LOI with some sacrificial surfactants and things like that. So kind of a long story short, we think that the LOI and SO3 are parallel problems, and if there is an LOI problem, it has to be separately addressed and beneficiated.
Thanks. There is one more question from YouTube I'm picking finally. This one is interested in what will be the impact of ultra fine fly ash? Let's say, can we conclude what will be the implication on conclusions?
Well, ultra fine fly ash is, I mean, I think if you have a high sulfur content at a high fineness, then that sulfur is what we expect it to become more available faster, kind of increase the kinetics of the solution by increasing the surface area. So if there is any area where we see that the excessive sulfate or excessive SO3 is causing problems, we expect that problem to be exacerbated. But otherwise, I mean, if the question is more general in terms of the ultra fine fly ash is, of course, is tend to be more reactive than regular fly ash, and more effective in providing the pozzolanic properties, ASR mitigation, et cetera, assuming that it has the right composition and it's kind of fits the specification limits for the most part in terms of the alkali and LOI and things like that.
Yeah, again, thanks for this work on developing novel admixtures for ASR mitigation. That opens a new line of research. And you will see more activities, I think, in this direction. Now, any other question? Those who are here, please unmute and ask. We can just take couple of more questions. Okay. There are no other questions. Really thank Mr. Farshad Razaripo for taking time for this lecture, excellent lecture. Anyway, this lecture will be made available on YouTube, and we'll send you a link so you can share that with others. And I again apologize for this issue to those who could not join our YouTube stream. Definitely will share this recorded lecture once we edit this. Thank you all. Thanks again for your time.
Yeah, and I also want to say thank you very much, Dr. Chansoli, Dr. Santanam, and Dr. Getsu for this excellent opportunity, and others, and for everybody's attention. Here is my email address. Feel free to email me if you come up with questions, or if you were interested in this in any way in future. Thank you. I appreciate it.
Thank you, Farshad. Thanks a lot.
You.
Thank you, Gopa.
Thank you.